So, welcome to this summer school, and I thought we should start off the summer school by, first of all, giving a little bit of motivation for quantum gravity and see why physicists or anyone might think that we need a quantum theory of gravity in the first place. And then also discuss some of the implications this may have, particularly for philosophically minded people who are interested in what kind of implications it may have for the metaphysics of space and time, for instance, or for other problems in philosophy. And we will see, this is a whole week, of course, about these sort of things. On the one hand, how quantum gravity can fertilize philosophy and traditionally philosophical questions, but perhaps also the other way around, where traditional philosophical methods can be used to perhaps even accomplish some sort of progress in quantum gravity as well. Okay, so this will be a little bit the second part of the particular survey, which is just giving you some of the sort of things that you will see come up again and again during the other talks in this summer school, as well as in the groups. The groups will address a number of these questions there. Okay, anyway, we just celebrated the centennial of general relativity. And of course, given that anniversary, you might think, well, what about GR in its second century? What is going to be the future of GR for the next 100 years? GR is, as I'm sure you know, actually a very well confirmed theory. In a certain domain of applicability, in certain kind of phenomena, it's a phenomenally successful theory. But there's no directly contradicting empirical evidence that would go against GR. So why would we want a quantum gravity, any theory going beyond GR, if there's no sort of empirical disconfirmation of GR? At least not in a direct sense. So more specifically, why would we think that we need a quantum theory of gravity? Now, it's important to make one distinction here. There's a distinction between quantizing gravity and formulating a quantum theory of gravity. A quantum theory of gravity, at least as I use the term, is any theory that combines gravity with the quantum aspects of matter. That may take very different forms. Quantizing gravity is one form this might take, of course, and it's probably the one form that most people think is the way to go, but it's not necessary, so it's important to make that distinction. Here's Richard Feynman, who was maybe the first one to really draw attention to that distinction. He said, look, quantum theory doesn't quantum theory as it was known back then, without quantum gravity in the sense we have it today, doesn't absolutely guarantee that gravity has to be quantized. So there's nothing intrinsic about quantum theory or quantum physics that means gravity has to be quantized as well. I would like to suggest that it is possible that quantum mechanics fails at large distances and for larger objects. Now, he was very clear that this was just a proposal. He wouldn't probably even bet much money on that, on not quantizing gravity. But it's something that is a possibility, at least. Now, so there are people who then have argued, well, no, if you accept the demand for a quantum theory of gravity, one reason that you would want to have to go back beyond GR and formulate a more fundamental theory, you then have to quantize gravity. It follows. There's a number of reasons you might think that's the case. And here's some literature for those of you who are interested. One reason you might think that you need to quantize gravity, given that you accept the demand for a quantum theory of gravity, is that there has to be some sort of a unification. All of physics has to be treated in a unified way. All the forces in particular have to be unified in the sense that they all get the same treatment in a unified theoretical framework. Now, 2 points. First of all, that this is the case, of course, is not an a priori truth. It may be an a posteriori fact, but it's not something that we can just sort of assume is the case of our world. The world, alas, may be dappled. And no such unification is forthcoming, even though, as people, defenders of that idea of unification often point out, there have been 3 or 4 instances in the history of physics where unification was extremely successful, so by induction, we should do it again. Well, that's a relatively small inductive basis, so who knows. And also, there's something wrong-headed, at least on some way of thinking about GR, about considering gravity a force. Some people say, particularly those people coming from relativity, that gravity is in fact not a force. So it's in some sense very different from the other forces. Therefore, you might have reason to think that it doesn't necessarily need the same treatment. So that's not conclusive. It may be suggestive to some, but it's certainly not a conclusive reason. There's a famous thought experiment from the 1970s by Epley and Hanna, where they have tried to set up a measurement setting where you're trying to measure incoming, gravitational waves, and then you had either a collapse or not a collapse, and then you could show that either way, either you violate momentum conservation or some sort of correspondence principle. So that was suggestive again, but again, that theory, that thought experiment was not conclusive because, of course, it contains a number of points at which you can get off the boat. You just say, well, I don't subscribe to this, I don't subscribe to that, I don't think that a collapse interpretation of quantum mechanics, for instance, is the right way to go, etc., etc. Then there's another famous argument from later on, which as an idea has been around, I believe, since the 1940s, but was probably find the sharpest expression in the 1990s by Dr. Wüthrich and Hartmut Roberts, where the idea is that if you try to measure any space-time region, spatial distances, temporal duration, that has a certain small scale, whatever measurement you want to make of that, if you try to make it so precise as to squeeze in photons or some sort of other particles to measure that, the size or the scale of that region, you have to concentrate so much energy or so much matter that it collapses into a black hole. So if there's just a certain scale, and you can calculate what that scale is supposed to be, where it's just not possible to probe the structure of quantum gravity at the more fine grain. Now, that's true, that there is that problem, it seems, but of course, that itself doesn't mean that space-time is really discrete. It just means that we can't measure it beyond a certain scale. But it's an additional inferential step that you can resist from the fact that you can't measure anything smaller than a certain scale, that space-time is in fact discrete. Okay, there's another argument by Perez and Terno, in some sense the most interesting one perhaps, where they try to formulate quantum and classical mechanics in a formalism that would, in some sense, allow for both quantum physics as well as classical physics, so-called Koopmanian formalism, so you can sort of cast classical mechanics almost as if it looked like a theorem of Hilbert space, and to sort of use the same sort of formalism to do that, and then show that if you have some sort of interaction between a classical gravity sector and the non-classical quantum matter sector, you're going to get into some problems such as, again, a violation of the correspondence principle, and so on and so forth. Anyway, there too, even though all of these arguments in some way are suggestive, none of them is really conclusive. All of them make, of course, certain assumptions that you can reject. Now, just from the fact that it's not necessary that gravity has to be quantized, of course, it doesn't follow then that the wider question has to be, shouldn't be affirmed either. So that still means, or can still mean, that we need a quantum theory of gravity, even if it doesn't have to be the quantization of gravity. Now, why would you think that? Or why, in other words, do you think we should have to go beyond GR? Why is GR not enough, as it were? Well, one reason people have given is because of singularities. As we all know, singularities generically show up in GR. It's not the case that they're sort of artifacts of a very high degree of unrealistic degree of symmetries in some spacetimes, as it was initially thought. It's really something that generically, under reasonable assumptions, happens both in gravitational collapse and in cosmological models. You have an initial singularity under rather benign and generic conditions. So singularities in some sense really are a physical prediction of GR. There's little way around that. And people have said, so for instance, the very eminent relativist Peter Bergman has said, well, you know, GR has these, because of these predictions of generic singularities, GR contains the seeds of its own destruction, because we cannot possibly accept as fundamental a theory that has singularities. Singularities, physics doesn't make sense anymore. The mathematical equations you get are, you know, show infinities. You can't do physics anymore. So therefore, there has to be something beyond GR. Well, again, it's a feature that at least older generations of relativists had trouble accepting as part of a fundamental physical theory. I think more recent generations of relativists are probably a little bit more easy about accepting singularities as maybe part of a fundamental theory. Now, it could be, for instance, that these singularities really point to something physical. There really is, in a way, that's the end of the world. There's nothing beyond that. It really, you know, there's no physics to be had at the singularity and beyond. So in a sense, it could be that that prediction is a correct prediction. So in itself, the fact that there are singularities is not quite enough to really force us beyond GR. And here's another reason people have given sometimes. They have said, because we need a sort of a generalized version of the second law of thermodynamics, therefore we need to go beyond GR. Here's how that argument is supposed to go. It starts from the recognition that black holes may be, which again are another generic prediction of GR and something that we believe we have observed, that has been confirmed empirically, that there are such things as black holes. Now, black holes, it seems, may violate the second law of thermodynamics. How is that supposed to go? Well, if you have a black hole with an event horizon, and you can sort of dump in entropy packages, and as soon as this entropy package goes beyond the horizon, boop, it goes and it's done. And it's sort of, the entropy is destroyed, right? If that's the case, the entropy of the universe could, of course, decrease. And that might be a violation of the second law. So what's been argued then is that the second law has to be generalized. It has to be generalized to not just include ordinary entropy, but also some sort of entropy of black holes that compensates for that loss of entropy if you dump in entropy packages into a black hole. So, in other words, black holes have entropy, have a form of entropy. If you postulate that black holes have entropy that can grow if you dump in entropy packages, then the overall accounting of entropy in the universe can, of course, still be such that it never decreases and the second law is saved. That's the idea. Now, usually from ordinary thermodynamics, we're used to the thought that if some system has entropy, it has microstates. That's what gives rise to entropy. And therefore, if black holes have entropy, then they presumably have some sort of microstates. That is, there's some sort of ways in which they can be in different states that do not macroscopically necessarily distinguish themselves from one another, such that the black hole can still have the same mass, the same angular momentum, the same charge, etc., etc. Well, not etc., so that's it. And because GR says a black hole, that's really the only thing a black hole can have. So Wheeler has coined the term that black holes have no hair for the fact in GR that black holes really only have mass, angular momentum, and charge, and nothing else. A black hole is completely described by these three parameters. So there's nothing additional to say. So they're very simple objects in some sense, according to GR. But if they do have microstates, then of course that would no longer be the case, and they would have hair in that sense. And that would be a violation of classical GR. So in order to understand the microstates of black holes, of course, we then have to go beyond GR, because GR is not going to get us that. Okay. Yeah, I think that's what I just said. So to understand the quantum nature of black holes, we need to go beyond GR. So that's the argument, the second argument. Now, the problem with this is, I mean, Carlo, I don't know whether you're planning to talk about this in your second lecture, perhaps, but the inference from that something has entropy to that it has microstates is also one that can be resisted. There could be ways in which you can assign entropy to a physical system without it having microstates. So that's one step in which the argument of the previous slide can be resisted. There are other ways in which it could be resisted. For instance, why should we believe that the second law of thermodynamics is a priori a fundamental law, something that's not violated when it comes to black holes? I mean, after all, we don't really have that much experience with black holes and how black holes interact with other physical systems. We have a lot of ideas of how it's supposed to work according to GR, but really, how much of a good understanding of black hole physics do we really have? Couldn't it also be at least a possibility that, yes, these things just violate the second law? That's not really a problem, because the second law was postulated as an extremely good law when we dealt with thermodynamic systems and terrestrial physics and sort of ordinary circumstances. And it turned out to have applications beyond the original domains of applicability, and it was amazing and as good as that goes. But what sort of guarantee do we have that black holes can't violate it? Well, I mean, a priori, no. Secondly, also, and this is the paper I'm currently working on, the original argument that was given by Jacob Bekenstein that black holes have entropy is, in my view, unduly depending on a sort of information theoretic approach to fundamental physics that I would want to resist. So, at least one particular argument that has been given for black holes having entropy can also be resisted on sort of more philosophical grounds, if you want. Okay, so if that's the case, then that in itself, the need for, or the alleged need for a generalized second law in itself is not sufficient to really force us beyond GR. However, there's one tiny, teeny little fact that really concludes the case that we need equality of gravity. We have absolutely overwhelming evidence that matter is not classical. Matter is quantum. I mean, this is what physics has found out for more than 100 years. If there's anything we know in physics, it's that. And GR assumes that matter is classical. So it cannot possibly be the final word. We have to learn how to connect quantum matter to gravity, whatever gravity is, in one way or another. And that itself is really a conclusive reason that GR cannot be the last word. We have to go beyond GR. So if you accept that, I guess two things, that GR is a theory that assumes matter to be classical, field or not, that's not relevant, but not having any quantum features, and that you accept that matter is, however, quantum, then you should be with me that we need some sort of quantum theory of gravity that combines these two facts. Good. So now that I hope we see at least one, I think, conclusive reason that we do need to go beyond GR, and a lot of other suggestive reasons, but not conclusive reasons. How should we go about it? So we have GR, very successful theory. We need to go beyond GR. What do we do? How do we find that theory beyond GR? Well, that's the sort of the holy grail of theoretical physics, or much of theoretical physics for quite a while. So of course this is not a question that I'm just going to answer. But we might wonder what sort of things should guide us in that quest. One problem, of course, is that unlike for most of other events in the history of physics, we don't really have empirical guidance. I hasten to add, other than all the physics we've already measured and confirmed, and the empirical data we have, which is quite substantive, of course. There's quite a lot. However, none of that sort of seems to directly point us to what kind of theory we have to be looking for. So there's not much guidance. Unlike in many other episodes in the history of physics where there was a clear direction given by empirical data, we don't really have it here. Many have looked to black hole thermodynamics as a sort of an important stepping stone to quantum theory of gravity, because as we've seen, even though it may not be completely conclusive, there's actually a lot of suggestive reasons to think that black holes really are interesting objects that might be the key to understanding quantum gravity, because clearly they're gravitational objects, they're strong gravitational fields, so relativistic effects are important, of course, and they may have quantum aspects, and as such, they may really be the key to our understanding there. In particular, the Bekenstein-Hawking entropy formula that for the entropy of black holes has often been accepted as an important test for any kind of theory in quantum gravity. Now, the original derivation, they were all done really, there's a number of different ways in which you can do it, in semi-classical gravity, which is one sort of straightforward way to combine quantum matter with classical gravity. It's like the first step to formulating a quantum theory of gravity. Now, one interesting sociological remark is that if you know, I've been following quantum gravity for a while, and I've met many different physicists who pursue very different research programs in quantum gravity, and they seem to disagree about a lot of things, about which fundamental principles should be assumed in the construction of the theory of gravity, which sort of principles are the relevant principles in quantum mechanics or in general relativity, in known physics, established physics, and so on and so forth. But they seem to agree that this is a test they should meet. As far as I can tell, all approaches in quantum gravity try to derive that formula. And if they succeed, and to the extent to which they succeed, that's considered sort of across, beyond their particular approach success. Okay. And this is remarkable because, of course, we haven't observed Hawking radiation. We haven't really any direct empirical evidence that black holes are thermodynamic objects with entropy described by this formula. There are people who try to build analog models. I think you're probably going to talk about this in Rodin's group, where there's sort of an indirect, and by analogical reasoning, you can have some reasons to think that there is Hawking radiation in black holes. And again, there's a lot of suggestive arguments, but it's not being directly seen. So that I find remarkable that nevertheless people agree on this. Anyway, good. So, semi-classical gravity. Is that then what we should do? Because that's in a way the most straightforward way to combine quantum matter with gravity, right? How does it work? Well, in my brief exposition here, I rely primarily on Bob Wald's classic introduction to the subject, which unfortunately is a little bit dated, so there are some things that have happened in the past 20 years, but I still think it's an excellent book. So what's the idea? The idea is to resist the temptation to quantize gravity. Gravity is a classical field. You keep it classical. So the framework of GR is used. What you do, however, is that the matter fields that you assume are quantum fields, and they propagate on curved spacetimes. That's the idea. And the quantum fields, the dynamics of those, of course, is going to be described by some quantum field theory. That's the idea. What you then do is how you couple these quantum fields, which have their own dynamics, to the gravity is through the so-called semi-classical Einstein field equations. So this is how they look like. So some of you have seen this, others not at all. Let me just very briefly say what it says. So this, the left-hand side of the equation, that's what Einstein called the marble, the beautiful form perfected part of the equation, which gives you the structure, the geometrical structure of space-time, and which encodes, in some sense, gravity. On the other hand, we have this mathematical animal here, which is a quantum thing. So this is, as a matter of fact, the expectation value of the stress energy tensor here, which is understood as an operator on some appropriate physically reasonable state. So what you do is you take the quantum states and you average out, you look at the expectation values only, and the expectation values in some sense are classical objects, can easily be combined, or at least more easily be combined than with the classical gravity. That's the general idea. That's the template of what you're trying to do in this approach. Now, it turns out that in some simple cases, this can actually be done with full mathematical rigor. If you have linear quantum fields in curved spacetimes, you can do that. Now you might think, oh, great, we're almost done, right? Isn't that what we wanted, right? This is a quantum theory of gravity. That at least for some cases we know and have some good control over it. Well. Don't get excited just yet. Unfortunately, as it turns out, there's a number of problems and limitations of this approach. And there are many. Here's just a sort of a selection. And I apologize to any one of you who's an expert in semi-classical quantum gravity if this is not quite up to date. I recently got challenged by a physicist, Wüthrich in Germany, who works on semi-classical quantum gravity, and said that the list of problems I'm proposing here is outdated. That's semi-classical gravity as of 10 or 15 years ago. They've solved all the problems he was suggesting. Now, well, anyway, let me just tell you what the problems are, at least as of 10, 15 years ago. So first of all, there's a problem because there's no unique sense of parallel transport anymore. There's a problem in the definition of this animal. Now, there's some ambiguities. There's different ways of doing that. And so you have an ambivalence. Is it this or that way? What's the right way to do it? Now, here's one way to do that. In case you don't quite know how to do your theory, you go to a more fundamental theory, right? Which then, if you look at the appropriate limit, gets you the right way to do the semi-classical stuff. Fair enough. I mean, presumably, if we had a fundamental quantum theory of gravity, then we could resolve those ambiguities. But of course, the point here would be to say, no, we want to try this as a fundamental theory. So there cannot be any hope in that sense for a more fundamental theory. Now, it turns out also that it contains sort of back reactions onto itself, and that means it will have certain pathologies. It has certain runaway characters. So these are not mathematically well behaved in some cases. And now, it's true, and I think this is the point in particular where Wüthrich was challenging me. It seems, I mean, again, I haven't followed the very latest in literature, but it seems like some of these things can be controlled mathematically. But the problem is, if some of these pathologies can be, under some circumstances, which are sufficiently benign, be controlled, is that enough to let you make generic predictions, to use the theory to make generic predictions? And as far as I can see, that's not yet the case. Again, Wüthrich and others might disagree with me, but I think that's still a problem. to use it as generic, for generic predictions. And that's sort of, marred by a second kind of problem, namely that in general we can't really compute that thing. So abstractly, the framework is there, but concretely, when you want to actually do concrete calculations, it turns out to be highly non-trivial in many cases. Furthermore, recent work by Empirical has shown that so energy conditions really are, it seems, important in classical GR because they give us a sense in which sort of models in GR are physically reasonable and seem to satisfy certain important conditions, which, by the way, are used in almost all the important theorems that we have in GR. There's one energy condition or other that's often assumed. Now, it can be shown that energy conditions, or the way they could be translated into the semi-classical picture, are generically violated, according to Empirical, under what seem to be very physically reasonable and relatively benign situations. If that's the case, how do you have any control over which models are physically reasonable or not, and whether anything analogous to these theorems in GR will hold in a semi-classical theory, or even within the limit, the classical limit. Of course, it's a measurement problem, people have said, is not solved, even if some of these technical problems are addressed, there's still a measurement problem, how to think how to think of, how to interpret the quantum bit of that theory. So all these problems, which are not all technical, I guess, at least the last one isn't, may well reflect that there's some sort of deeper problem. If you think about the Riemann tensor and how you can sort of make a distinction between Ricci curvature and Weil curvature, which is one way to distinguish between the gravity and the matter part, and then you quantize one part but not the other, that seems sort of kind of unprincipled. Why that part and not the other part? So it's maybe that's just, there's something wrong with this idea that you run into all these problems. So if that's the right diagnosis, which is a bit tentative, I have to say, but if that's the right diagnosis, then you're just not going to get to the theory you want along that road. It'll be some sort of intermediate steps, perhaps, to a full quantum theory of gravity, but that may still be needed. Here's another thing that has recently been much discussed, the so-called firewall paradox. Now, the firewall paradox is an argument that has been thought, for instance, by Raphael Busseau, to have, if it's a sound argument, giving you a menu from hell, as he called it. You have three options, three poisons. You have to drink one, at least, and presumably you don't want more than one if you don't have to. So it's a bit the situation like in Bell's theorem. You really start out from things you think are, from assumptions which you think are obviously true to something which is demonstrably false. So you have to get rid of one of the assumptions, and each one hurts if you have to give it up, right? You have to accept non-locative some form or other there as a result of that, and here, if the argument is sound, then it seems to be sort of a similar dialectical situation. And here are the options. The first option is the dynamical evolution from matter falling into a black hole to the outgoing Hawking radiation is not unitary. So any quantum physicist will say, oh, well, but I mean, this is a basic rule that has been satisfied. Otherwise, your theory doesn't even make sense. It's sort of very, very, very basic fundamental assumption of how we think of any quantum physical theory. So that if that would have to go, that would really hurt. The second option is some form of the equivalence principle is violated. Now, that's where the relativists start to scream and say, no, but the equivalence principle, come on. The equivalence principle is such a central pillar of GR, and we have such excellent confirmation of the equivalence principle. You know, we can't give that up, right? It seems like that would hurt as well if we had to give that up. Now, I think that's, it's maybe too early to tell because this is really just, 3 years ago, in the past 3 years that people have debated these options. But I think the majority of physicists would favor giving up number 2 here. And by thinking that, an event horizon, rather than what the equivalence principle would suggest, namely that you could it's a theory, it's a place, as it were, where you can sail through without noticing. So if you dive into a black hole, you won't notice anything as you pass the event horizon. And if that's rejected, then you can think of the event horizon as a firewall. You burn up on the event horizon in a wall of fire. That's why it's hence the name of the paradox. So, okay, that would certainly have implications for how you think of black holes. The third option, however, is to think there's something wrong with the semi-classical approach, the way we've been mixing and matching classical and quantum principles here. So something about that is not quite right. Maybe we have to change the way we do that. Now, mind you, that's also going to hurt, even if you think semi-classical quantum gravity has the problems it has, in the previous slides. That's still going to, it seems like, oh, but come on. We know that quantum field theory on Minkowski spacetime is a good theory. That's something we have pretty good control over, and for a number of important physical cases, excellent empirical confirmation. Now, you think you take that Minkowski spacetime, you change it a little bit, right? You don't make it a really crazy relativistic spacetime, just a little bit. Why should not be something almost like QFT on Minkowski spacetime still be the perfectly right way to do physics? And then it seems like, well, but you should have on at least a very, very slightly curved spacetime, something that is not too far away from this. So that would kind of hurt as well, because then we would have to relearn how to do that in other fundamental ways, perhaps. Okay, but it's an option. And as an option, if you want to take that horn, that may give you an additional reason to reject the way semi-classical quantum gravity has been done, and to go for a full theory and then try to get to the full theory. And then from that, try to come back and understand how that regime can be understood, of course.
Here, by reject, you mean reject as a fundamental, complete solution of the problem, not reject the approximation. That's what you mean. Well, to get a firewall, you need this to be true exactly, not to be true.
Yes, that's right. That's right. Yes, that's right. Yes, yes. But it seems like can't you get arbitrarily close to it? So yes, that it would have to be exactly true, of course, but couldn't we get as close to exactly as we wanted? Anyway, so that's sort of the dialectical situation. So I think what we have here is, let me go a little bit quicker because I'm realizing it's almost 10 o'clock. So we find ourselves in a situation without...
Start 10 minutes late.
Okay. Well, but I don't know whether they will be serving lunch 10 minutes late.
Well, we have a coffee break between.
So we can have a short
So we can
break.
skip lunch?
No. Drink coffee quickly.
Anyway, so, we don't have much empirical guidance. That may change as we expand our empirical horizons. There's a number of people who work on quantum gravity phenomenology. Some of them have interesting ideas. Maybe, human ingenuity is not to be underestimated. Somebody comes up with really excellent ways of sort of indirectly or looking at very large systems or very old systems where you sort of see collectively amalgamated quantum gravitational effects percolating to the sort of things that we can actually measure. It's possible people are working on that, and that would of course be very, very helpful. Now, it may really be that black holes give us the key to make the next step there. And it may be that we need a bolder approach to quantum gravity, which you will hear this week about at least two main ones, about loop quantum gravity and string theory. So these are theories which, of course, go beyond semi-classical gravity, and they have the ambition to give you a full quantum theory of gravity. Okay. It may or may not be necessary to reproduce the Bekenstein-Hawking formula. There may be corrections to that, depending on how we think then of the semi-classical regime coming from the fundamental theory. And one thing we do know, whatever we do, we need to reproduce GR in one way or another. GR, given that it's been empirically so well confirmed in a certain domain for certain phenomena, we better be able to capture that again. Okay, now, so that was the motivation part. We have some motivation to look into quantum theory of gravity, quantum theories of gravity, and try to come up with something new to say there. Now, physicists have been working on this in a number of different directions, disagreeing with one another about almost everything, developing rather different theoretical approaches to quantum gravity. One thing, as philosophers that we've done, Nick and I in our project and some others have done, is to sort of study these different approaches. And one thing that you sort of see generically in one form or another is that something interesting happens to space-time in these theories. Somehow, space-time isn't just there anymore in the way it used to be in the fundamental ontology of the theory. Space-time somehow gets really radically changed or completely eliminated from the fundamental theory. Now, let's see. So I guess this one, that's what I wanted to say. So these theories, they presuppose or entail, that depends a little bit on the dialectical direction here, that there's a sense in which space and time are not there. It's important to see that the denial of the fundamentality of space and time and the radicality with which that's denied differs from approach to approach. Because the structures that are fundamentally posited in the different approaches are pretty different. So that's important to say. But if that's the case, then space-time theories such as GR become effective theories. They only effectively describe something that's really not fundamentally there. Space-time itself is an emergent entity then, or at least relativistic space-time. Much like in thermodynamics, you have an effective theory, and temperature is an emergent thing that somehow arises from the collective degrees of freedom in the way they interact. Now, space-time then may be something that really arises only in those circumstances in which the fundamental degrees of freedom collectively interact in the right sort of way to give rise to something that looks to a very good approximation like a relativistic space-time. Okay, so that's the picture. You have fundamental stuff that gives rise, and here is a similar picture, something like that. Anyway, now here's one immediate philosophical worry that you might have. A worry that has been articulated in the context of so-called wave function realism, as Alyssa, for instance, has been working on this, where if fundamentally you don't have space-time, four-dimensional space-time or three-dimensional space or something like that, can your theory still be empirically coherent? It's not inconsistent, it's something sort of a milder charge than that, but still pretty bad if borne out. What's the charge? Well, the idea is that a theory is empirically incoherent just in case the truth of the theory undermines our empirical justification for accepting it as true. I take this definition of empirical incoherence from Jeff Barrett's book about many worlds theories, and it's become pretty standard to use now. So there may be a theory, and it may be true, but if true, the world would be such that we would not have the right sort of, we could not have the right sort of justification for believing it to be true, assuming that we're in the business of empirical science, that we want empirical justification for the theories we hold to be true. Specifically then, a theory denying the fundamental existence of space-time is thus, would be alleged to be empirically incoherent because, the empirical justification of a theory derives only from our observing effects of a localized something situated in space-time. There have to be something like local variables. You observe the coincidence of a pointer and the scale, or maybe the right flashing of a light in your lab, or something. Something happens somewhere at some point in time. In your lab, Friday afternoon, 3:20, you observe this here, right? So that's in the most general form, the form of empirical data that we have. And the theory, if such a theory were true, there could be no localized something because there's no space-time. Then you're in trouble. How could you possibly have empirical confirmation for such a theory? Okay, that's sort of the immediate philosophical worry that you're led to. Now you might think, oh, but come on, that's not really a worry. Well, yes, Nick and I didn't think that it's ultimately really a worry that should stand, and we've written a paper about that, and I think this will be further discussed in some groups as well, I hope. So, if the theory, as space-time-less as it may be fundamentally, nevertheless admits for an emergent space-time in the appropriate way, at the appropriate scales, arguably, then it could be shown that, that there's no problem with that, because you can, at the scales at which scientists operate, at which physics labs exist, etc., you can still have the appropriate form of localization. Now, this is a very important task. So the getting back, recovering of something that looks very close to general relativistic space, and it may not have to be identical with general relativistic space, but something that's very close to general relativistic space. If you can get that back, the worry seems to be dispelled. I mean, maybe there's a little bit more work that needs to be done, but that would at least be a crucial part of that work. Now, this is important anyway, because as I said before already, and I hope you would agree, that whatever the fundamental theory of quantum gravity is, it will have to recover GR in the appropriate approximation or appropriate limit, because GR has been so successful. Or something at least that to the extent to which GR has been confirmed has to be indiscernible from GR. Make the same sort of predictions. Thereby it would explain why GR was as successful as it was to the extent to which it was successful. So that's a sort of a criterion that is generally valid in physics. This is why Einstein was very excited, or first worried, that he couldn't recover Newtonian gravity in the appropriate limit, and then was relieved to see that he could, at least to his satisfaction. That's exactly the reason, because the prior theory you want to replace has been successful, and you want to be able to explain why it has been as successful as it has been. Now, it turns out that's really part of the hardest work for any quantum theory of gravity, to really get back GR in the appropriate sort of way. That's not trivial. A lot of approaches are really struggling with that. And I come to what I believe is my very last slide. So this is space and time after quantum gravity. This fact that space-time seems to disappear alone gives us a very rich menu for philosophical consideration, also for technical problems and challenges for these different approaches to try and recover GR. And this is a sort of a central theme, as you will see, of course, of the summer school here that we're having, the reason why you're here. The project, the Templeton project, which funds this summer school and our activities, and also a co-authored monograph that hopefully will appear next year, right? So this is
Hope
part
we
of.
finish writing.
I guess that's a necessary condition. Yes. Yeah, that's the hope. It comes out of my work as well. Yeah, anyway, so that's the book we're trying to write, where we look at various approaches to quantum gravity and see how space-time disappears and how it can sort of be recovered, or at least what the best story that physicists in that camp tell us of how it can be recovered. Okay, and this is superficial, I understand that. There's many details to be filled in, but I should give you a little bit of a taste of what we're going to do here this week. Thank you very much. So, how long do we have for questions?
So at least 10 minutes, right? 10, 15 minutes. And have to go over a little bit and have a little off the... Oh, we have 20 minutes.
So,
we were supposed to go to 10:30, so...
Really? Oh, right,
yeah,
okay.
20 minutes.
In mine was not. Oh, good.
You want another slide, you want?
No, actually, that is the end of my
But
slide.
that's really great if we can have a little time, 10 to 20 minutes at the end of each talk for discussion. And
Yes. I was
especially
planning
for
to
the
have
students
that,
that
but
like
unexpectedly I'm
questions.
having it now. Okay, so I think Rodney, Jesse, yeah.
So, why should space-time disappear?
Why it should?
Yeah, no, I mean, it's one thing that the theories that have been proposed have that feature. It's another whether we have any independent reason to believe that it should disappear.
I don't think we have reason to believe that it should disappear. We have reason to believe that something interesting is going to happen to it, I think. Because, you're looking at relativistic spacetimes, we try to formulate the quantum theory of these things. Whenever we moved from a classical theory to a quantum theory, something interesting happened to the system that we redescribed in quantum physics, right? So presumably something interesting is going to happen there as well. But other than that, I don't think there's any sort of a priori conception that it should disappear or something. It just turns out to disappear in a number of ways and different approaches.
It's just really interesting that it does disappear in the different approaches in some sense. And I was just wondering whether it's like there are some like independent framework, independent reasons in some sense. Well, one could understand that.
Can everybody over there hear the questions? It's a little echoey. Okay, just make sure everyone
So
speaks
do you
up.
want to have a response to that? Okay, yes, please.
Well, first of all, should it means two things, and maybe it's my weak English, but it might mean it has to necessarily, it must, and it might mean it's likely to. So the first meaning it has to, I don't think, drop the question, that was the next one. Why is likely to, and why it actually disappears in various approaches? So I think it's very simple, the reason, which is the following. In general relativity, a four-dimensional space-time is a solution of a dynamic, of the equation of motion of a dynamical system, which is the Einstein equations, which is the general relativity itself. So it's a trajectory of a system, and in quantum mechanics, in not all, but almost all, except in Wüthrich perhaps, formulation of the theory, you don't have a trajectory of the classical object. So the first thing you do when you go from a classical particle to a quantum particle, except in the Wüthrich, is you give up the idea that there is an actual particle moving in space having a position at each time. So if you just take this simple idea and you move it to general relativity, you take away the simple idea that there is a full metric that we want to time which is well defined, so you don't have a four-dimensional space-time anymore. I think it's only that which then percolates into the different approaches and different languages.
So you mentioned that one of the strange things about semi-classical gravity is that it quantizes matter, but not space.
Yes, of course, it's somewhat strange. So the first one is generally considered perhaps a necessary but certainly not sufficient condition. So for instance, there's an approach called causal set theory, where you basically assume that the fundamental structure is a discrete causal set, meaning partially ordered by a causal precedence relation, and it's discrete. But that's still considered a classical theory. It's a discrete theory because they think that's a first step towards a quantum theory, but because it doesn't have any quantum dynamics or any of the sort of signature quantum effects, the mere fact that it's discrete is not sufficient to say that this is a quantum theory of gravity. So more needs to be said. It's not complete the program there. And then yes, once you do actually have truly quantum effects of space-time, it becomes very hard, and it seems as if like the floor is taken away from underneath you, quite literally. And then this in a way is what makes quantum gravity so hard. And yeah, as you will see, at least for two main approaches this week, there's different ways of trying to address that and trying to think about that. So, yes.
Yeah, I was just curious what the way you did this initial tension with local variables, empirical, and coherence. So can we translate, every time you said fundamental existence of space and time, just replace that with fundamental spatiotemporal properties? And the reason I was thinking this is, on the current formulation, it sounds like something like a relationist possible physics would not have any local variables.
Why would the relationalist?
Well, if you think there's no fundamental space, there's no fundamental space-time, like something like Barber, for instance, would his view have local variables?
Fundamentally, it seems no.
And is there supposed to be so for instance, does his view lose out on, is his view supposed to be empirically equivalent? It just seems like something like Barber's view shouldn't.
Every theory which sort of fundamentally, at the fundamental level, doesn't permit sort of localization seems prima facie to have this problem. And something needs to be done to address the problem. You have to show that in some way or another, you can have localization or sort of good enough localization at certain scales at which you need them for the sort of empirical testing you do. That's the idea. So any theory that fundamentally doesn't have space-time, like Barber's, it's the same problem. How do you get back the local variables or something that looks close enough to localization? Yeah. You have a figure on that?
I don't agree with it seems like the concern with when you get these in sort of empirical coherence is where you don't have three-dimensionality or four-dimensionality. And so whether your metaphysics of space-time is whether your substantive Krebs relation list, you might not have objective locations, but you still have these relative locations in three-dimensionality. So you can still say, well, there's a Geiger counter click at this distance from me, and that's enough to get your observations. So I don't think whether you're a relationalist or substantialist matters. The worry is that you have a loss of four-dimensionality, the kind of four-dimensionality you have in GR.
Yeah, no, just relationalist is not enough to get the word, because you can have perfectly. I thought there was more to that, not just relationalism.
No,
if it's just relationalism, then I think.
It just sounds like maybe the formulation right now is too strong, because all you need to get the tension going is a lack of sort of fundamental spatiotemporal properties, whether those are defined over some substantial manifold or just relations between discrete bodies. Seems like anything. So I'm thinking as a data that if you have something like Barber's view, where the sort of physical correlate or whatever is making an observation, and the Geiger counter, and we have sort of spatiotemporal product relations between those, that view can't lose out on this empirical adequacy or empirical coherence thing. So whatever our formulation of the initial puzzle should render those views okay.
Yeah, So I mean, the problem is that for very often for quantum theories of gravity, the dimensionality goes as well, and quite a bit of the sort of spatial temporal usual spatial temporal structure that we would need for localization goes as well, and has to be recovered again from the fundamental theory to a sufficiently good approximation, at least, that we have the usual kind of three-dimensional or four-dimensional localization that you need. So what you see often in a number of approaches is, for instance, that the dimensionality, which is a tricky thing to define if you have these weird structures in the first place, but if you come up with some sort of magnitude that tracks to a sufficient degree what you take to be the dimensionality of the structure, then you see that it's often, if they're very small, it's two-dimensional, and then it goes up or down, and then it's sort of, only for sufficiently large, sufficiently well-behaved states, it approximates the usual three-dimensional space or four-dimensional space-time, things like that. So that's, in a way, it's a slightly different problem, of course, than the wave function realism case, but the dimensionality is normally not built in at the fundamental level as well. It's not 3n dimensional or what have you, but it's some other dimensionality than the usual one we have. Yeah. Okay, I think Tom has a question.
Yeah, I have a very similar question, so I'll go to the end of it.
There were other hands, yes.
So after reviewing some of the problems, you said that the conclusive reason to go to quantize gravity was the matter is quantized. Like you said, that was like the main reason for pursuing this project.
Yes.
But I was wondering, so if GR assumes that matter is classical, and we have confirmed very well that GR, shouldn't that be also a reason to suppose that matter is at the end and continues, and we have to do something to obtain like the other way around?
Oh, I see. Just because GR is such a greatly confirmed theory and it's a classical theory, there must be something wrong about the quantum description of matter, because classical theories, after all, are so successful. I don't quite think it's symmetrical, I guess. I do think that there are a lot of empirical results that, any way known of coming up with a classical description of matter have failed to make the correct predictions for these experiments, whereas quantum mechanics has spectacularly succeeded in doing that. That's a really pretty conclusive reason to not try to insist on a classical theory of matter. Now, and the same doesn't quite hold the other way around. It's not as if we have a big body of evidence or experience or observation or something that, the classical theory of gravity, it's gravitational phenomena that the classical theory just can't describe correctly, gives systematically the wrong answers. That's much more questionable and if anything indirect. And yes, as I said, many people believe that once we go to black holes or to the very early universe, that changes. Then we really can't describe it. Can't make the correct description with the correct predictions with the classical theory for those things anyway. But the data is not quite as firm as in the other case. Did you have a figure on that?
No, it's a full question.
Okay, then I will go to
Just a really quick question. So I don't know the set classical graphic literature, all that was really something to address forward. When you talk about sort of quantizing the matter section of the field equations, you take the expectation value of the stress elements. In order to define classical stress energy density, you still need a metric. So it doesn't seem to be sort of straightforwardly the case that what you're doing is just quantizing just the matter bit, because you're still getting some kind of geometric or some kind of space-time geometric object in the thing which you're then quantizing and you're then making operator value. The question is, how does the semi-classical approach deal with that? What does it have to say?
Well, that part is still classical.
But you're taking the expectation values of the operator value, presumably stress energy tensor, and that has in order to define it, you need the metric. So what happens is does the metric then somehow kind of factor out of the?
That's a good question. I don't know the answer to that. I'm sorry. Do you know?
It's just you treat it like you would another classical, and you multiply it by a metric of C number.
It's the same. It's fixed. It's not an operator. It's just. There is one concern with the semi-classical theory taking as fundamental, not as an approximation, which you don't have addressed, or maybe you have just addressed when you said measurement. I don't know, but I'm curious to know what you think about, which is the following. It seems to predict strange phenomena, which we wouldn't expect, like this one. Suppose I have a particle with charge and mass, and a speed, and I do a Stern-Gerlach. Okay, so it can go up or down, depending on the speed. Now, if between up and down we have a little charge, classical, heavy stone charged, what we see in the laboratory is that half of the time goes up because spin was up, so there's a trajectory up, and half the time goes down because the Stern-Gerlach went particle. The Stern-Gerlach particle measures spin down, so the particle is here, so it's attracted by that. Okay. Now, suppose I just have a mass here. So it's attracted gravitationally. Now, if you use your equation, what happened is that you have a wave function of the Stern-Gerlach particle, which is half here and half there. So the expectation value of the mass density is half here and half there. So the mass is not attracted neither up nor down. But the phenomenology of Newton attraction and Coulomb attraction are same in any possible respect. So why should they become so dramatically different in that context?
Yes, I mean, I don't have anything to say to that other than this is an additional reason to think that it's somewhat artificial and unprincipled and not according to our expectations, that there should be this principled distinction between the Ricci curvature, as it were, the Weil curvature with the gravity of the matter part. That just that's not warranted as a fundamental theory. As an approximation, it may be fine or not. I mean, that's a separate question, but as a fundamental theory, it seems like it's not.
Oh, so you would take this as a sort of a hint not to take it as a fundamental theory?
Yes.
Yeah.
This was, by the way, this was not meant to be an exhaustive list. This is just some highlights of the sort of problems that you get.
So it's kind of failure of unification.
Well,
that's the idea, right? That gravity isn't fully in the quantum comparisons. In a way, it's just highlighting what the semi-classical approach says. On one side, it is just going to stay classical.
That's true, but the point is, that it goes beyond sort of just a metaphysical a priori demand for unification. These arguments show you that if you do make such a distinction, it's unnatural in a worse sense, because you can't give a coherent account of these sort of cases. For instance, and yes, you can ask yourself what the principal distinction should be between the Weil and the Ricci curvature and questions like that. And so it's not just sort of a demand for unification and treating everything in the same way. It's the attempt to show that if you do not, you run into certain very specific kinds of problems.
But what Carlo said in particular seems just sort of highlighting the lack of unity.
It highlights that, and it gives you a physical reason to think that this lack of unity is really a problem.
Yes, there is behind this there is a distinction between certainty and high plausibility. I mean, what am I certain of about the physics on the basis of what I know? Well, nothing. So everything could happen tomorrow morning, but on the basis of induction from and from reasonable, would I consider it reasonable that something so dramatically different happened from the Newton interaction and the Coulomb interaction? I guess that what I'm saying is that perhaps the totality of physicists would say, oh, come on, this is not going to happen. And if I had money to bet on an experiment in laboratory, I would say 99.9 against 0.1 that the Newton interaction in that particular case would behave like the Coulomb interaction. Does this prove that? No, of course.
John?
I had a question about the file, the takeaway points from the elimination section at the end. So the last two, the fourth was when we have to reproduce the segregation and we don't. But we definitely need to reproduce GR. And I was wondering whether you had something in particular in mind with what it would need to reproduce GR. So if you asked me to do it, I would say, oh, well, you look at the classical theory, you do analytical analysis, you usual sorts of approximations, and then the expectation values you get out of that should match up with your quantum theory, at least approximately. But if you do that analysis with the classical theory, and you assume that you have a Lorentzian metric, then you're going to get Hawking radiation. You also assume it's Einstein dynamics, then you get the Lorentzian equation. And so it seems like if you mean reproduce GR in the way that I would think quantum physicists would, then it seems like you're going to have to get that.
I was thinking of it in more basic terms than that. I mean, if that's the way in which we recover GR, then yes, I guess that sort of comes for free that you get that as well. But I don't think there's anything necessary about that. There could, in principle, be different ways in which you get. Just think of GR as a classical theory. Don't think already sort of quantum and how you get to the classical theory. Just think of GR and what its sort of predictions are about geometrical magnitudes, really essentially of space. And what that means is you need to get something like that matches this sufficiently well. Whether it's a quantum theory or not, whatever it is, it has to explain to the why GR general relativistic effects are get the right sort of results for your GPS calculations or things like that. That sort of thing you need to get that. How you do that? Well, I don't know. That will depend on the particular approach. Yeah, but I mean you're right. And if you think of it sort of going through this sort of something like semi-classical GR, so then that seems hard to avoid. Okay, so Martin and Nick both have a finger.
Because we've kind of had this conversation to get back GR. It's not pleasing to get back every solution of GR.
Oh, no, not at all. Yes, that's a good point. No. As a matter of fact, I would certainly not expect that we get everything back in GR. GR is a very, very permissive theory. It gives us all sorts of things where it's questionable whether it's physically reasonable, whether it's physically relevant, things we certainly haven't observed, all sorts of crazy stuff. So that would be way too strong. Something, what we get back has to be much smaller than that, much sort of weaker than that. And of course, the fundamental theory is going to correct GR in a number of ways, we would expect, saying that, there may be some violations, for instance, of the Einstein field equation within a certain degree of, difference for certain cases. There may be and so on and so forth. You know, we get certainly corrections to GR, and we get something back to GR. But to the extent to which the GR is empirically confirmed, and for those sort of things for which it is confirmed, we should be able to recover that. So for instance, yes, we should be able to recover something that's to a very good approximation, like the general relativistic calculations we need to get the GPS signals right, and things like that. If we don't do that, then we have not succeeded yet. That's the idea.
I think we should wrap it up.
Okay. Okay. Yeah. No, that's an important point. So this is really shorthand for something like GR, sufficiently like GR, in the appropriate sort of regime for those sort of things for which GR is a non-confirmed theory. It's certainly not just GR. So maybe I should have made this clear by saying GR star or something, or GR minus, or something like that has to be recovered. I mean, of course, there's going to be corrections. Like for classical physics, in a classical description of matter, there's at some point where that description gives out. That's why you want a quantum theory. Of course, that's going to happen here as well. Anyway, yes, I suppose.
All right. Thanks, Chris.